So it's not the computational complexity doesn't belong to the real world problem itself, it's the mathematical model that we came up for it. So it's possible that our mathematical model can be changed to answer that specific question that the client or the customer or the person who is paying us to solve this particular problem is looking to do. So let's consider our mathematical model and then see if that model itself has some lower bound, and if that's the case, then what else can we do to figure that out? So I'm actually just rewriting the problem that we wrote a little bit ago. So the problem we have is same. This is called, now I'm defining it a little bit more formally now. It's called the metric K-center problem. We are given n cities with specified distances. Cities are locations, and we want to build K warehouses in different cities and minimize the distance of each city from its closest warehouse. So it's the same minimax problem, I'm just writing it again. The fact that we call it a metric K-center problem, the metric comes from that this the space that we have satisfies the regular triangle inequality. So if the distance from here to Chicago is x, the distance from Chicago to LA is y, then if the distance from here to LA is z, then x plus y is greater than or equal to z, right? So you can't have it that it takes from here to LA something less, but something more, but if you go from via Chicago, you actually are covering less distance. So in the real world, this is quite a realistic kind of an assumption, but it's not always the case. Can somebody give me an example where it's not, where our usual sense of metric doesn't work? And and this is a little closer to us than we might think. If I'm not talking about time travel and Einstein, I'm just talking real things that we deal with every day. Or we heard of rush hour, right? So sometimes you go from here, depending upon how you do it, you can actually cut back on traffic. Okay, I'll not teach you how to break the law, but let me give you the example of Canada, right? If you fly from here to Canada, or if you fly from, sometimes it's cheaper to fly to Canada via London. It takes a little bit longer, but it's cheaper. I've done that. No, I mean, I've seen that. I haven't actually done that. I saw that, and I said, okay. So if you want to fly from here to Calgary, you actually have a better chance of, you could go from here to London, fly back from London to Calgary, so it happens. Of course, you've seen that while buying air tickets, that it happens all the time, that it's more expensive to go to the place which is actually on the way of the place that you're going to. If it's cheaper, right? So if you buy a ticket from here to LA, it might be costing $500, and that has a stopover in Colorado. But if you try to buy the ticket to Colorado, it's $700. So you can try to do it. You can say, okay, I'll just buy the ticket to LA and then stop over. Except they don't let you, then you cannot fly back. So the world is a little bit more complicated. So this is our mathematical model. And now that we are talking about a mathematical model, we are not under this problem. We can actually now try to come up with understand the complexity of this specific problem. Well, it says here that the problem is NP-hard. I wasn't aware, but fine. But can you tell me why would this problem be very hard, like NP-hard? I wasn't aware that the answer was right on the slide. So tell me, why would this problem be NP-hard?
You can verify it in
polynomial time. Okay, good. So let me say it this way, that if the question said why is this problem NP-complete, then you would have to say two different things, right? The problem is NP-hard and you can verify it. So we know we can verify it. If we can verify it, then, and I'm not sure whether we can verify that or not, but let's focus on the NP-hardness part. Why is this problem NP-hard? So again, one of the prerequisites for this specific lecture is that we understand all those concepts. I'm not covering them again, but I'm looking for ideas and what might be able to prove. What does this problem look like? So when we want to say that problem is NP-complete or NP-hard, what is the usual modus operandi? What do we try to prove? So what do we try to prove? Chris, go ahead.
That there's a column in NP that can be reduced to this problem.
There's a problem in NP complete.
In NP complete.
In NP complete set that can be reduced to this problem, right? So, okay, so Chris has laid it out for us. So how would we say, based on this problem, what does this problem looks like closest to anything else that we have covered? Well, let's see what problems did we cover when we talked about NP complete problems. We talked about satisfiability. What else? I'll take notes right here.
Click.
Click problem, okay. Okay, preset.
Independent set.
Independent set, okay.
Vertex cover.
Vertex cover, okay. What else? TSP, Hamiltonian cycle, Hamiltonian path, okay. Okay. So what does this problem sound the closest to? Well, let's see the example and see if that brings us any. Okay, so for example, what is this problem?
Vertex cover.
The vertex cover. So the vertex cover. So this problem looks awfully close to a vertex cover problem. I'll give you 30 seconds to a minute to think about what might be a reduction to the problem here again. What might be a way for us to think of a reduction from vertex cover to our problem, right? That's the direction we want to prove, right? Not from our problem to vertex cover, which will prove nothing, but we're saying that if we have a solution to this problem, then we can solve the vertex cover problem quite easily. Okay. So what are the ideas? Derek, what's the idea? Well, maybe I can just suggest that one thing is here is that this, what seems to be the case is that this problem is focusing on the distance, right? And the vertex cover has nothing about the distance. It's only trying to say if there's a vertex cover exists, right? So how might we be able to make a leap from the vertex cover to this problem? So our outer box looks like in the QR paradigm. Our outer box looks like that we are given a vertex cover. We're given a graph and we're given an integer k, and we are asked, does this graph G have a vertex cover of size k? And we have to give a yes/no answer to that. And we would like to use a solution for this particular problem, the metric k-center problem, and be able to answer the yes/no to the vertex cover. We can ignore the metric portion for now because that's only the edges that's only the weights on the edges portion, and the vertex cover says nothing about that, so we can ignore whether it's metric or it's not metric.
So you take the graph and pass that in with k being the number of warehouses and say, is there a way to have vertex